So our next test is the limit comparison test, often abbreviated LCT. I've written up what the full test is here. So let's suppose that AN and BN are positive sequences. Uh, if they are, then what we can do is calculate the limit as n approaches infinity of their ratio of AN over BN. And we can get a conclusion that if L is a positive number but not infinity, then AN and BN both behave the same way. In other words, they both converge or they both diverge. If L is equal to 0, then we have sort of a narrower conclusion, which is that if BN converges, then AN converges, and if L equals infinity, then if BN diverges, AN diverges. Uh, you can't, for example, if L equals 0 and BN diverges, you can conclude nothing, and if L equals infinity and BN converges, you can conclude nothing about AN. So the essentially what this is saying, and we saw this actually in the case of improper integrals. There was also a limit comparison test that worked pretty much like this. Essentially, what this is saying is that if I carry out two sequences far enough, in other words, regardless of what they do initially, we have x, 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 then x, 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 like that. These are just two sequences that I'm trying to define. But essentially what this is saying is that if I carry the sequences out past this purple line, eventually one of them just becomes some multiple of the other one, and that multiple is L. So what that means is that it makes sense to say that if one of these sequences adds up to a finite number, then the other one is just some multiple of that finite number, which is also finite, and likewise for infinity. So that's why it is that if you get a number between L and between 0 and infinity, a positive finite number, it makes sense to say that the two series are going to behave the same way. The L equals 0 and L equals infinity cases are a little bit less intuitive, and we'll see them more rarely. In general, you're going to be making the most use of this part of the theorem. And like I said, it works essentially the same as the limit comparison test that we already encountered for improper integrals. So let's do a limit comparison test type of problem. Let's determine whether the sum from n equals 1 to infinity of 1 over the square root of 4n squared plus 1 converges or diverges. The first part of any of these sorts of problems is developing the intuition about what the answer is. In other words, you want to be able to look at the problem and say, okay, I figured out what the answer is and how I'm going to prove this. That's not a complete answer. You have to actually then use the limit comparison test to prove it. But what that means is that I have to choose something to compare this series with. I have to choose something that I know that I can compare it with, that I know has a property of convergence or divergence. The way you do that is this. For the limit comparison test, what you want to do is focus on the highest powers in the numerator and the denominator. In this case, that's 1, which is 1 times n to the 0, and square root of n squared. We can actually ignore, although we couldn't do this with the direct comparison test where we had to form a proper inequality. For the limit comparison test, one thing that's really nice is we're actually going to be able to ignore the coefficients. So I can really say that 1 over the square root of 4n squared plus 1 is basically, I realize that's an imprecise term, it's basically 1 over the square root of n squared, which equals 1 over n. There are a lot of things wrong with that statement. I can't say that it's approximately equal to this because I'm ignoring this 4. I certainly can't say it's exactly equal to this because that's not correct algebra. And there's not really a good way to say why it's basically this expression, but the point is that when we consider what happens as n approaches infinity, the general sense of this expression is going to be completely dominated by the highest powers, which is why I've ignored everything else. I've ignored the coefficients, I've ignored the constants, I would ignore lower powers if there were any of them. So basically, this is what the series is. This is what gives us Bn to compare to. So this is going to form An, and that's going to be Bn. So now that I know what I want to compare the series to, let's state that we're using, I'm going to use a different color. Let's state that we're using the LCT, and let's say that An is equal to 1 over the square root of 4n squared plus 1, and Bn is equal to 1 over n. I can now calculate the limit as n approaches infinity of an over bn, which equals the limit as n approaches infinity of 1 over the square root of 4n squared plus 1 over 1 over n. This is going to be more convenient if I write it in this form. If I write an, instead of an over bn, I'm going to write an times 1 over bn, the reciprocal of 1 over n, which is just n over 1. So that equals the limit as n approaches infinity. For positive values of n is equal to the square root of n squared, so that's going to equal the square root of n squared over the square root of 4n squared plus 1. I can multiply that now by the square root of 1 over n squared over the square root of 1 over n squared, and that equals the limit as n approaches infinity of square root of 1 over the square root of 4 plus 1 over n squared. That's going to equal, by substitution, I get square root of 1 over square root of 4 plus 0. That's going to be 1 over the square root of 4 is 2. So there's the limit. Now, what does the LCT theorem say? It says that if I get a limit between 0 and infinity, in other words, a positive number that's less than infinity, when I get this, I can conclude that an and bn, that the sum of an and bn behave the same. So first of all, let's verify that the condition for the LCT is met. We can say that 0 is less than 1/2 is less than L. That's true. Therefore, the sum of an and the sum of bn either both converge or both diverge. And by the way, note that I need the sigma here. I'm not making statements about what an and bn themselves do. I'm making statements about what the sum of an and the sum of an do. Now, we can say in this case that the sum of bn diverges because the sum of 1 over n is a p-series with p equal to 1, which is less than or equal to 1, and I can say, therefore, the sum of an diverges. End of proof. So we've answered the question and proved our result. By the way, you'll learn in the textbook that this series is called the Harmonic Series. And it's just as correct to say that the harmonic series diverges as it is to call this a p-series with p equals 1. So anyway, this is a proof under the LCT that the given series diverges.